Okay, we're going to look at this acceleration versus time graph problem. I know the majority of you are having trouble with finding the position, and that's what we're going to focus on. If I were to go through every single step on this problem, it would take very, very long. I know that mentally you'll skip some steps, and I'm going to do so as well. So if you get lost, just pause the video, think about what I've done, and that way I don't have to talk for 20 minutes straight. Okay. So the idea is that you want to set up a velocity versus time graph. A sketch of this is going to help you solve the problem. How do we transition to this velocity versus time graph? Well, we need to look at the area under the curve. So if we were to think about the area of, say, right here in the box that I've drawn. Why are we looking at that box? Because the first set of questions is asking about things happening up until 3 seconds. We only care about that area up until 3 seconds. The area of under the acceleration versus time graph represents the change in velocity. So this area here, we could go ahead and calculate. It's 3 times 7, or 21 meters per second. What that means is if you start out with an initial velocity of -9 meters per second and add a change in velocity of 21 meters per second, then we're going to be at a velocity of 12 meters per second. And that's the answer to our first question here. It's not 21, it's not -9, it's the idea that you're adding some change in velocity to an initial one. The next part is where most people get stuck, and this is where our sketch is going to help us out. Because we realize that in this sketch of a velocity versus time graph, the area shown underneath this curve represents a displacement. So the area under this curve is a displacement, and if we could find that displacement, we'd be able to answer this question. The one problem, we don't know this time here. And because this is a sketch, we don't even know, we can't even make an estimation. All we know is it's between 0 and 3. So how are we going to find that? We need to set up an equation for this line. You can think about the equation for a line in terms of y equals mx plus b. So the equation of this line is going to be v 7 meters per second squared. How do I know that? Because the slope of this line is the acceleration. T minus 9 meters per second. If we were to solve this for v equals 0, we'd find the time where this crossing point occurs. So doing that, it's just a few steps of algebra. You get a time, and I'll have to round this a little bit, of 1.2857 seconds. That's this guy right here. So now we can think about calculating the areas of, say, this triangle here, which I'll call 1, and this triangle here, which I'll call 2. So the area of 1, or the displacement caused by that first section, is 1/2. The base is 1.2857 seconds times -9, the height, meters per second. For the second one, it's going to be 1/2. Now, how do we think about this length here? This is going to be 3 minus that time you just found. And this height here is positive 12. This is going to give you two areas. You can go in and calculate them. But if you were to calculate these out and then add this area plus this area, you would get a total displacement of approximately 4.5. Again, I'm skipping some steps just so we can keep the video reasonably short. But you're welcome to work out that math yourself. So this is not the answer to our question. This is just simply the displacement. The question is asking what is the position. Remember, the position can be found by taking some initial position plus the displacement. So if our initial position is, let me make that a little neater. Our initial position is 10 meters. We're adding a 4.5 meters displacement. So our current position at 3 seconds is 4.5 meters. Alright, so let's erase this and repeat the process for 8 seconds. So for 8 seconds, we're going to now need to make this box a little bigger. We need this to include up to 4 seconds. So we've got a little more delta V here. The delta V of this box is now positive 28 meters per second. So starting at -9, adding positive 28 meters per second, we have a current velocity of 19. Now we need to think about the area from 4 seconds to 8 seconds. Calculating the area of that curve, 4 times -6, gives an area of -24. So that's going to take us from 19 minus 24 meters per second, takes us all the way down to 5. So this tick here occurs at, let's add some more labels. This tick here occurs at 4 seconds. We remember that our crossing point was 1.2857 seconds. We calculated that earlier. We don't know this crossing point, but we know right here is 8 seconds, and right here is -5. So that answers one question. The velocity at 8 seconds is -5 meters per second. Simply taking the initial velocity and adding these two changes of velocity tells me that. Now we have to perform a similar game to find this crossing point here. That's another difficulty, because if we think in terms of y equals mx plus b, there's something we don't know. We don't know the vertical intercept. Now we can imagine extending this line, and this line could be described as having a vertical intercept, but we simply just don't see it on the graph. So thinking in terms of that point slope formula is not particularly useful. Instead, we want to think in terms of another formula for a line. I'm sorry, this is point slope. The previous was slope intercept. So we want to think in terms of point slope. So we can calculate this line. Our y is v. Let's pick any coordinate on this line. I'll go ahead and pick the coordinate 4 seconds, 19 meters per second. So minus 19 meters per second equals, the slope of this line is -6. This is 4 seconds. Oh, I'm sorry. The slope of this line is -6. X is t. Our x coordinate is 4 seconds. And just like before, we're going to set v equal to 0. So we're going to set v equal to 0 and solve for t. That's going to require a little bit of algebra, and make sure you distribute that -6. That's an easy mistake to make. So we have -19. So that's going to be a time of 7.167 seconds. Okay, so now we got a little bit more work ahead of us. We're going to have to find the area of this triangle, this triangle, this triangle, and this triangle here. I'm going to go ahead and refer to those as 1, 2, 3, 4. I'm going to pause the video here for a moment. And here's my work showing the calculation for the displacement of each of these 1, 2, 3, 4 triangles. If we were to add all these displacements up, we would get a total displacement of positive 48 meters. Again, that's not our final answer, because we need to take the fact that we began at an initial position of 10 meters and then add that displacement. So 10 plus 48 gives a current position of 58 meters. As I said, pretty involved problem, but you just need to walk through the steps yourself. You'll gain a lot by doing that. So I'm going to, if you want to stick around, I'm going to show you another way to do this problem. All we need is the fact that, I deleted it, but the fact that at 4 seconds, our velocity was 19 meters per second. The other thing we'll need is the equation. This is generically the equation for the area under a velocity versus time curve. Even though we don't see the velocity versus time curve, we can still think about it here. This would be like the triangular part, any linear portion, and this would be any rectangular part. Okay, so this is less thinking involved. You don't gain as much from doing it this way, but it still works out. So the idea is that we can find the displacement of each of these two boxes. So we'll talk about this one first. So the displacement of this box would be 1/2. The delta V from this box, if you remember, is positive 28. And the change in time over this box is 4. The initial velocity at the start of this box is -9. And again, this is 4. If you work that out, you get a displacement of 20 meters. Okay, now we think about the displacement from this box. This change in velocity is negative, and that is a negative 24. The change in time in that box is still 4 seconds. The initial velocity at the start of this box is 19 meters per second. That's why we needed this. And the time again is 4 seconds. Calculate that out. You get 28 meters. So what does that mean? The displacement from this portion was 20. The displacement from this portion is 28. So we have a total displacement from each of those portions of 48 meters. Ring a bell, because the displacement of 48 meters plus the initial position of 10 meters gives us this. But basically, you don't learn anything by doing it this way. That's why we're avoiding it. This should just seem like magic to you for the most part. Maybe you see where this equation comes from. If you do, that's good. So I really think it's worth the time to sketch that velocity versus time graph and calculate it the way I've shown you, but this is kind of a fallback to if you just can't get the numbers to work out that other way. Anyway, you can give me an email if you're totally stuck and I'll help you out. Alright, thank you.